Problem 108, we want to find the minimum value of f of x, and we're not really sure what this graph looks like. So we have to use some calculus methods, and one of the methods that we learned how to find the minimum value is just to take the derivative. We can find mins and maxes. And so f prime is equal to the first function multiplied by the derivative of the second, plus the second function multiplied by the derivative of the first. So we have 1 plus ln x. That's f prime. Okay. Well, f prime equals 0 when 1 plus ln x is equal to 0. In other words, when ln of x is equal to -1, and so therefore e to the -1 is equal to x. So that's our only critical point. So we know right there that we have a horizontal tangent line right there at when x is equal to e to the -1. Okay, keep in mind that because we're taking the ln of x in the original function, we know that the domain of the original function is that x has to be greater than 0. When we conduct our f prime test, we have 0, and then we have our e to the -1, and then that's it. That's our only critical point. That's where, again, where f prime is equal to 0. And so to the right of e to the -1, we should be able to tell pretty quickly that f prime is positive on that interval, okay, which means that f is increasing on the interval. And then on the interval from 0 to e to the -1, there's a bit of analysis that goes along with that, but you should be able to determine that f prime is negative on the interval from 0 to e to the -1, okay, which means that f is decreasing on that interval, and so we can see the minimum value. Since f is decreasing and then increasing forever, it never comes back down. The minimum value that f of x attains is not e to the -1. That's the common mistake that many students make. They say, oh, e to the -1 is the minimum value. No, that's the x-coordinate of the minimum value. So f has a min at e to the -1, but f of e to the -1 is equal to e to the -1 multiplied by ln of e to the -1. And so where should we put that answer? Let's put it right here. So right underneath it, e to the -1 is 1 over e, and ln of e to the -1 is just equal to -1. So the answer is that the minimum value that f of x attains is -1 over e. That is the answer. Okay. Well, 110, we just did 108. All right, well, let's go ahead and scoot on over here to do number 109. 109, we're given the graphs of f prime, and f prime is the parabola, the blue graph, and then f double prime is the straight line. And we should be able to tell that f prime is like a negative x squared. So negative x squared, was that like plus 5? F double prime then would be equal to the negative 2x. Okay, so f prime is here, and then f of x is a third degree polynomial, but also it's in the negative direction. So f of x should look like that. It should look something like this, where the ends of the graph go down from left to right. So that's what f is going to look like, and we have to go right through point P. Okay, well, we already see point P there. It's already darkened in for us. And a couple things. We know that f prime is equal to 0 right here and right here, whatever those x values are. So if f prime is equal to 0, that means that we have a horizontal tangent line at those values. And then we know that f is concave up, so this is f prime positive, f double prime, sorry, positive, and so f double prime being positive means that f is concave up on the interval from -infinity to 0. So for all values of x that are less than 0, f is concave up. So for all values of x that are greater than 0, so for positive values for x, we're going to find that f is concave down because f double prime is negative on that interval. Okay, so let me back up a little bit so I don't clutter up my drawing here. But again, we've got concave up, then concave down. We have an inflection point right there at when x is equal to 0. We also see that f prime is positive on the interval from negative, in between the two critical points, is positive. And then we see down here that f prime is negative on the before the first critical point and after the second critical point. And so what does that mean? Well, that means that f is increasing from negative infinity to this value here, and then decreasing, okay, increasing in concave up though. Whoa. Increasing in concave up. I knew there was something wrong with that. So right down here, f prime less than 0 means f is decreasing and concave up until we get to this critical point. Okay, and then past that, increasing and concave up, and then increasing and concave down to the right, and then what do we have past here? Past this one, it's decreasing and concave down. So we already knew what it was going to look like. I just wanted to confirm, and I didn't put it through point P. So point P is actually the inflection point. So let's do that. So we know then that the horizontal tangent line is going to be down here somewhere. We don't know where, but we know that f is decreasing and concave up on that interval, increasing and concave up on the interval from the critical point to the inflection point, and then we have increasing and concave down like that, and then decreasing. Let me erase some of this stuff. Let me get rid of some of that. Okay, so again we have f decreasing and concave down, decreasing and concave down right there. And so how does that look? We've got horizontal tangent line. I was a little off on that. Over there, horizontal tangent line here corresponds to the x-intercept of f prime. This one corresponds to the other x-intercept of f prime. And then what else? What else? And then we have the point P, which is the inflection point, because again, f double prime changes from positive to negative at 0. So there you go. That's what the graph would look like. That's the graph of y equals f of x. Alright, and I'll clean this up over here a little bit as well. And can we, yeah, we have a little bit more time here, so let's go ahead and do numbers 110 and 111. The graph of the second derivative of f of x is shown on which interval or intervals is f of x concave up. So again, we get a second derivative graph. Down here, second derivative, where are we? Down here, second derivative is less than 0. Up here, second derivative greater than 0. And down here, again, less than 0, second derivative. So the second derivative we see at q changes concavity. So f double prime less than 0 to f double prime greater than 0. Okay, to f double prime less than 0. So what are we looking for? On which intervals is f of x concave up? Oh, so all we need is concave up. That means between q. So between q and s, f of x is concave up. Remember, this is the graph of the second derivative of f of x. And if we're looking at the graph of the second derivative of f of x, that gives us information about f of x. So that's what I said from the very beginning. We're going to be looking at f prime and f double prime and answering questions about f of x. So when f double prime of x is above the x-axis, and when f or when f double prime of x is greater than 0, we have f of x being concave up. So on the interval from q to s. Okay. And finally, we've got this limit here as x approaches -4 from the left and from the right. Actually, sorry, this is just from the right. So as x approaches -4 from the right, we know that when x is greater than -4, so for all values of x greater than -4, so if we plug, let's say, a -3 in here, -3 plus 4 is 1, -3 plus 4 is 1, absolute value of 1 is 1, numerator is 1, so everything's 1. Okay? In other words, the graph to the right of -4, it just looks like that. And let's say this is 1 right here, here's y equals 0, sorry, x equals 0. And then we have 1, 2, 3, 4. And anyway, the limit then is equal to 1. It's like way past my bedtime right now, sorry. 1 is the answer. So that's it. 1 from the right. From the left, in case you want to know that, from the left, the limit would be -1. So as x approaches -4 from the left, the limit is -1. So the limit as x approaches -4 from both sides, there would be no limit. The limit would be non-existent. Okay, that's it for that one.